Hey everyone, welcome to another episode of Generating Conversation. My name is Vikram Srikanti. I'm the co-founder and CEO of Aqueduct. And as usual, I have Joey Gonzalez here with me. Joey, do you want to say hi?
Hi everyone, thanks for having me again, Vikram. Happy to be here. Quick intro to me. I am Joey Gonzalez, faculty at Berkeley, co-founder at Aqueduct. Been doing research in machine learning systems for over a decade, built parts of Apache Spark. More recently, I've been thinking a lot about kind of the prediction infrastructure, taking models to production.
So we've spent a lot of time on this series so far talking about LLMs and everything that they can be used for and why they're so awesome and why everyone's so excited about them. But throughout, we've also alluded to a bunch of the sharp edges, the limitations of LLMs. And anecdotally, we hear about a lot of these things, of both about LLMs and foundation models, where they can fail in one of many ways. And so I'm curious to hear more about what are the limitations of LLMs and foundation models that we know about. How come, models like GPT hallucinate sometimes? How come some of the image models like DALL-E and Stable Diffusion struggle to draw fingers? What's happening here, and how do we think about these limitations?
Yeah, LMs have a lot of limitations. We're often so excited about their strengths, but forget about their key weaknesses. And you start with hallucination. That's a great example of one of the key limitations of using LLMs. You have to remember that they are a statistical picture of human knowledge language captured over billions of tokens. They're just predicting the next word. Based on a probability distribution. When we look at for language, the next word might not actually be the correct. The most likely next word might not actually be the correct next word. And so we will often see LLMs go ahead and continue to respond. What is give math an example. What is the square root of pi? And you go, square root of pi is 2 point, and just start making up numbers. And so it's because it has some idea of, when asked a question about math, the answer should be some math. It might have seen square root of pi, so it might get, pretty close because that shows up often in the corpus. But if you add some other random numbers, it's going to guess some additional random numbers. It's hard for it to reason about math itself. And so this idea of hallucination shows up not just in math, but in language in general. So it sees some, question about some people. It'll use those people in the answer, even if, they aren't actually the answer to the underlying question. So hallucination is a big problem. In computer vision in these stable diffusion models, one of the neat examples of hallucination is, as you allude to, is drawing a hand. Drawing a hand is actually hard for a human to do because hands have so many different poses. You have occlusions. They're just hard to draw. My daughter draws giant circles for hands because she kind of gave up on fingers altogether. Language models, the analogy in vision, the hallucination is, you see hands as textures, like bark on a tree. It doesn't have a concept of what really is a hand. It just has kind of different pictures of hands at different orientations. And so, when it's computing what a hand should look like, it's going from noise and going, I think I see another finger there, because a finger shove a finger beside it. And so you start to have lots of fingers coming out of a hand. There is just no good way to get clean hands. There's a lot of work to try to improve hand quality, to give models some knowledge of form and structure. But at the end of the day, they're making decisions locally about pixels, so it's hard to get these pictures right. So hands is an example of hallucination in vision. Other areas where these models fail, we often have to deal with biases. So the models are trained on very large data sets. Those data sets might have social biases. They might reflect the worst parts of mankind, not just the best parts. And so we spend a lot of time trying to address those. That's a hard problem in itself because we want to capture, nuance of language, but we also want the models to reflect kind of our better selves. And so, it's an area of active research to make these models better representation of the language as a whole.
You touched on how LLMs don't really know how to do math and sometimes spew random numbers out because numbers are the next likeliest thing to come out of the distribution. A related interesting limitation of LLMs is that they don't really know how to reason about structured data. You can't take a database table and feed it into an LLM and ask it meaningful questions about it. Why is that? What's happening here?
Yeah, so LLMs, again, embodying this kind of predicting statistical distributions of the next word, don't have the innate ability to do this kind of complex mathematical reasoning. Though there's some examples of them doing some basic manipulation. In some sense, like humans, we are also not great at doing lots of algorithmic stuff in our heads. We're perhaps more like LLMs in that we're like better at predicting what would come next in some logical sequence. And so using computational tools is something that there's a lot of interest in. And if you look at something like OpenAI, one of the early plugins they added was access to Wolfram Alpha, giving it some computational logical reasoning tools to address the problems of mathematics. An area of open interest for many is giving these same LLMs access to tools for reasoning about structured data in a more intelligent fashion.
Interesting. On that note, there's actually a lot of work that's gone into thinking about how to expand context windows for LLMs, right? I think a useful analogy here is kind of the context window is what an LLM can keep in its working memory at any point in time. And depending on the LLM and its architecture, there are different limitations, but roughly, I think it's like a few thousand words that fit into a context window. And we've seen vector databases, things like GPT Index have become really popular in the last couple of months, trying to solve this context window problem by, having these large retrieval indices that then narrow down what the LLM gets. Are these required pieces of infrastructure, both for structured and for unstructured data with LLMs? How important are they going to be?
It's a great question. So context windows, maybe the first thing one should know is that when predicting the next token, you look back at some sequence of tokens. That's usually your question, some prompt, maybe what in fact, often what the model's already written so far. That becomes all part of the context. If I want to ask a question about all of this data or this book that I'm trying to read right now, the model you can't stuff all that data in the context. And obvious question is, why not? Well, one, the context, the computation itself is quadratic in the length of this context. We spent a lot of compute already for these relatively small contexts, tens of thousands of tokens, is in fact actually a larger context for a lot of these models. So being able to extend that to entire books, large databases is not tractable. Another minor issue is that when we train these models, we need to have some data at different context lengths. And so getting these large contexts into our training data can also be expensive. And so when we want to use these models with interesting data sets that are much larger than can fit in the context to answer questions about large bodies of text, we often introduce things like retrieval, where given the question, we want to then find snippets of text that are relevant to that question so that the model can read that snippet of text and then answer the question more effectively. Kind of like a human, you can't read the entire encyclopedia to answer a question. You might want to zoom in on the important parts that are relevant to the question being asked, and then bring that information into your head while you go to answer that question.
Okay, so something that's been discussed extensively of late is reinforcement learning with human feedback, or RLHF. Why is RLHF critical to the success of the LLMs that we have today?
Yeah, so RLHF is used to align the models with humans' expectations of what they should do. In a sense, RLHF is a way of teaching a model to answer questions in an organized, logical fashion, to give it a goal, not to just complete a sentence, but to really answer a question.
Awesome. Well, we have a whole other conversation planned on RLHF, so I'm sure we'll get into the technical details quite a bit more there. But is there anything else we should discuss about the limitations of LLMs and foundation models today?
Yeah, I expect that we'll see lots of limitations coming out in the upcoming NeurIPS submissions in the next month or so. So I'm looking forward to reading those very soon. There's a lot we can definitely do to make these models better, and that'll be hopefully keeping us busy for at least the next few months or years.
Awesome. Well, thanks for the time, Joey.